This is my Precalculus course. Today we're going to review functions and function notation. If you haven't done the homework completely correctly from the last class, do that homework before watching this video. The reason we're going to do this is that functions are very important for upper math courses, especially calculus. So we're going to do a little bit of review on functions, and we're going to learn some new things that we didn't have time to learn in my intermediate algebra course. So let's review the basic idea of a function. A function can be thought of as a machine, as we mentioned in my intermediate algebra course, and we enter an input into the machine, and the machine processes that input and gives us some sort of output. In the case of mathematics, we're talking about numbers and operations on those numbers. So here's an example. The operations are squaring a number and adding 5, and the number that we enter in for x is the input, and the output is the number that we get once we perform these operations. So here's some examples. Let's say that the input is 3, so we plug in 3 for x, and we get 14. So we have our input, which is usually called x, and then we have our output, which is called f of x. We'll get to that later. If we plug in -2 into our machine, then we get 9. So 9 is the output, -2 is the input. That's the basic idea of a function. So you should be pretty familiar with this at this point in your math education, but we're just quickly reviewing. The most difficult thing when it comes to functions is the notation. The concept of a function, as you can see, is pretty easy, but the notation can be intimidating. F is the most common letter that we use to notate functions, obviously, because F stands for function. But here's where things get a little confusing. X is the input, as we said, and f of x is the output. F is the function itself. So it's kind of confusing when we say that f of x is the output. This is where the confusion lies. When we write the output in this form, it tells us what the function is that we used, and it tells us the input, and this expression represents the output itself. So this is very, very confusing. Again, this expression represents the output when we plug in x as our input into the function f. So this output notation again tells us what the function is, and it tells us what the input was to give us this particular output. And that's a lot to take in all at once, and so students get kind of confused, and we pronounce this expression f of x as it says here. Now notice we have parentheses here. So another characteristic of this expression here that makes it confusing is in previous math courses we learned that parentheses indicate multiplication. So it seems that we're multiplying f by x, but that is not the case. So we're violating the rule. The rule is when you see parentheses, that indicates multiplication. This is a violation of the rule, because now this does not mean multiplication. So you need to understand that math notation is not consistently used, and not every form of math notation makes perfect sense. Sometimes the rules are broken, and there's nothing we can do about it. It's just the way that it is. The same is true when it comes to any language. Sometimes rules are broken, and that's just the way that the language evolves over time. It's no fault of any particular individual necessarily. So let's give some examples here, or one particular example. So let's say that we have some function f and our input is 9. Well, then we can say that our output is f of 9. That's just the way that we pronounce the output and the way that we write it. Again, I know this is very confusing, but this is just the way that we do it. So let's say that our input is root 5 and our function is f. Then our output would be f of root 5, and so on and so forth. Let's say that our input is a cubed and our function is f. Well, then the output would be f of a cubed. So again, this expression tells us the function that we're using and the input that we plugged into the function, and it is notation that we use for the output. So again, that can get kind of confusing. So for those students who are very experienced with function notation, this is going to be pretty easy stuff, but we do need to review this, so let's go over this quickly. So let's say we have a function f of x is equal to 2x minus 5. We're asked to find f of 3, f of negative 4, and f of 0. So let's do some practice here. So f of 3 is this exact expression, no difference whatsoever, except instead of x, we plug in 3. So again, this is confusing notation, but the operations, as you can see, are very easy. So f of 3 is the output if you plug in 3 as your input into the function. So f of 3, the output, is 1. What this means is if you have some machine, and we're going to call it f, you have your machine, you're going to put in an input. In this case it was 3. Your output is going to be 1. We call the output f of 3. Again, I know that's very confusing notation, but that's what this means. So let's try to find f of negative 4. If the input of this function up here is negative 4, then the output is negative 13. So that's all that means. And let's find f of 0. So if the input is 0, the output is negative 5. Okay, so let's try one more of these. And it says here to fill in the table. So now we're going to fill in a table. Oftentimes you'll see tables like this. This is the input column, and this is the output column. So our function is defined to be this expression up here. So let's find f of negative 5, because it says here we want to plug in negative 5. So 10 over negative 5 plus 2 is the set of operations, and we get negative 2 plus 2 is 0. So the output was 0. So we wrote this exact expression down here, no difference whatsoever, except instead of x we wrote negative 5. because that's our input is negative 5. So if our input is negative 5 and this is our function, then our output is 0. So what that means is we can now plug in the output into the table 0. I'm going to write in red. So now let's find the output if the input is negative 2. So I rewrite that expression again, except instead of x, I write negative 2 because the input is negative 2. So negative 5 plus 2 is negative 3. So the output is negative 3. Again, this is review for most students who are at this level of mathematics. So now the input is 4, so I'm going to rewrite that expression up there. But instead of x, I'm going to enter 4 because the input is 4. So now we have 5/2 plus 2, which is equal to 4.5. So the output is 4.5 if your input is 4. Now this is kind of a trick problem. We're going to plug in 0, but 10 over 0 is an undefined expression. So the function is actually undefined when we try to plug in 0. And I forgot to write my output there, so that's 4.5 because we're filling in the table. So what you can do is write UND, undefined, when the input is 0. So again, this should be a review for you. You can take a picture of this this first screenshot here to help you, and you can use problems 1 and 2 to help you do number 3. I want you to get some practice with this, so please try number 3. When you come back, we'll do it together. Okay, we're back. So we're going to plug in 2 to that function, and whoops, we should get negative 5 for our output. 2 to the second power is 4, minus 9 is negative 5. So I rewrote this expression, no difference whatsoever, except I plugged in 2 for x, or I substituted x with 2. So now we have 2 to the third power minus 9, which is 8 minus 9, which is negative 1. So if you got that right, good job. F of negative 1. Now we have to use an exponent rule. So that is rule number 8, exponent rule number 8. Then we have to use rule number, I believe it's rule number 6 if I remember correctly. Anything raised to the first power is just whatever the number is. And then we have negative 8 1/2, or you can say negative 8.5. It doesn't really matter if you write it as a fraction or a decimal. So if you got those answers, very good. Now you're going to fill in a table. So I want you to fill in that table for number 4. When you come back, we'll do it together. Okay, we're back. So 3 minus 4 times the absolute value of negative 3. So that's 3 minus 4 times 3, because the absolute value of negative 3 is 3. Then we have 3 minus 12, which is negative 9. So I can enter in negative 9. That's the output if the input is negative 3 for this particular function. So again, I wrote this expression, except instead of x, I plugged in negative 3. So now, if the input is 0, let's figure out what the output of the function is. So I'm going to write that exact expression, except I'm going to replace x with 0. The absolute value of 0 is just 0. So we have 3 minus 0 is 3. So if you got that right, good job. So if the input is 0, the output is 3. So now we're going to plug in pi. So we have 3 minus 4 times the absolute value of pi. And pi is a positive number, so the absolute value of pi is just pi. So we have 4 pi. And we can just write it like that. You could estimate the answer, but it's better to leave it as an exact expression. So if you found an estimate, that's okay, but it's probably best to write it like this. So if you got that right, good job. So now let's plug in negative 0.6 for the input. Negative 0.6. So we have 3 minus 4 times 0.6, because the absolute value of a negative 0.6 is just positive 0.6. Then we have 3 minus 2.4, which is 0.6, or you can write that as 3 over 5. So if you got that right, good job. Okay, so that was just some basic review there. Now, we also need to remember that a necessary characteristic of functions is for every input, there must be only one output. If you enter an input into a function and you get 2 different outputs, then that machine, that function in the world of math is you're not really allowed to call it a function. So let's say that you have a machine, or a set of operations in this case. I mean, we can think of this as a machine, but let's say that the operation has a plus or minus symbol on it. Well, then you would get 2 outputs for every one input, because you have a plus or minus symbol. So that means that this expression here cannot qualify as a function. For example, if we plug in 5, then we get 14, but we can also get 4. So this expression cannot be a function. For every one input that you plug in, you can have only one output. For every input, you can only have one output. But in these examples, you have one input, but you have 2 outputs. We have one input, but 2 outputs. So again, these expressions do not qualify as functions. And one of the most common problems that you'll get, not necessarily at this level of math, but at the lower levels of math, you'll be given problems like this, which help you to demonstrate this principle. So in the tables below, X represents the inputs and Y represents the outputs. Circle the tables that could not represent functions. So some of these tables can represent functions, some of them cannot. So let's look here. So we have our inputs, and for each input we only have one output. And it looks like this is okay, but here we have 0 as an input and then 0 as an input again. But notice for 0 we have this output, but we also have a different output. So what that means is that if you plug in 0 as your input, you can get 1 or you can get 9. So that's 2 outputs for one input. That's not allowed. So this table could not represent a function. So I'm going to circle that because it says circle the tables that could not represent functions. So basically, the way that we do this is we look for repeated numbers in the input column. So here we don't have any repeated numbers, but here we do. We have zeros repeated. And let's look over here. Let's see if we have any repeated numbers. It doesn't look like it. But over here we have 7 repeated. If you plug in 7, you can get either 16 or 5. So that means that this does not qualify as a function. So these tables, they can represent functions though. So we don't circle those. Let's try another problem. So notice that we have -4 in the input column, and we have -4 again in the input column. Not only that, but we have 10, and then we have 10 again in the input column. So if your input is -4, you'll get 2 outputs. One output is 2, and the other output is 1. So this does not qualify as a function. Also, if your input is 10, you get 12, or you can get 1/3. So this table does not qualify as a function. This is very, very important to understand. So here we have -3 repeated, and we have 6 also repeated, so that does not qualify. And I don't see any numbers repeated in the other tables, so it looks like they can represent functions. So I want you to try number 7. Again, if there's a number that's repeated in the X column, then that means that most likely the table cannot represent a function. So try number 7. When you come back, we'll do it together. Alright, we're back. So there are no repeated numbers in the X column in this first table, but in the second table we have -7 repeated. And there are no repeated numbers in the X column here that I can see, so that qualifies, but we have 9 repeated here. So if you got that right, excellent. Try one more of these problems. When you come back, we'll do it together. Okay, we're back. So there are no repeated numbers here. There are no repeated numbers here in the X column, but we have 20 repeated, so that does not qualify. And here we have 3 repeated, so that does not qualify. We also have 8 repeated. So I didn't see 56 also. 56 is repeated. But all we need is 1 repeated number in the X column, and that disqualifies the table as a function. Now, there is something that can occur that's kind of tricky. If different inputs produce the same output in an expression, then this does not disqualify the expression from being a function. So, for example, if we plug in 8 into the function, we get 64 in this case, but if we plug in -8, we also get 64. That's okay. You can plug in 2 different inputs and get the same output. That's fine. But if you plug in 1 input and get two different outputs, that disqualifies the expression from being a function. So this is an example where we have one input and two outputs because we have the plus or minus symbol. So this expression cannot be a function, but this expression can be a function, even though we plug in different outputs and get the same, or excuse me, we plug in different inputs and we get the same output. In contrast, here we plug in one input and get two different outputs. That's not a function. So let's demonstrate with some tables. So notice here that we can plug in 6 or 0 and we get the same outputs. So there's a number repeated in the Y row. The number that's repeated is 2, but that's okay. Numbers cannot be repeated in the X row because then the table cannot represent a function. But if numbers are repeated in the Y row, that's okay, because that's this scenario here. So there are no numbers repeated in the X row. There are no numbers repeated in the X row here, but we do have numbers repeated in the X row here, so that means this cannot be a function. Now this does not disqualify the expression or the table. It's the -5s that disqualify the table from being a function. So let's look at this table down here. Do we have any repeated numbers in the X row? And the answer is we don't. Now we do have repeated numbers in the Y row, but that's okay. You can plug in a bunch of different inputs and get the same output. That's fine. There's nothing wrong with that. Okay, let's try another problem. Let's look for repeated numbers in the X column. We do have repeated numbers, but this brings us to another important point of confusion for a lot of students. We have a number that's repeated in the X column, so that would mean that this does not qualify as a function, but actually it does qualify because this is a trick problem. Notice that we have a 5, or actually a -5, in the Y column. If the input is -7, the output is -5. That's what this tells us. But down here, we have the same exact situation, so it's a trick problem. If a number is repeated in the X column, that usually means that the table does not qualify, but because we're tricking students here by writing the same output, actually this does qualify. Now -5 is repeated in the Y column, but that's okay. That just means that there's we have the same output for multiple inputs. That's fine. Again, what disqualifies a function is if you have different outputs for some input. So you plug in your input and you have more than one output. So again, we have the same situation here. 11 appears twice, so we would think that this could not be a function, but look at the outputs. They're the same output. So whoever wrote this problem is trying to trick us. So here we have the same input. We have numbers repeated in the X column, so we would think that this could not be a function. But again, the problem is trying to trick us because the outputs are all the same, so that means that that can be a function. Here we have numbers repeated, but again the outputs are also repeated. But what disqualifies this table as representing a function is we have 6 producing two different outputs, 3 and 8. So if you plug in 6, you get two different outputs. So that's not allowed. So these problems can be a little tricky. So again, if a number is repeated in the x column or row, then that indicates that the table may not be able to represent a function. But be careful, because if the input and the output are the same for multiple operations, multiple examples of the operations of the function, then that does not disqualify the table from representing a function. So try number 11. When you come back, we'll do it together. Okay, we're back. So we're looking for repeated numbers in the x row, and we do have repeated numbers. So you plug in 10, you get 7, you plug in 10, you get 3, you plug in 10, you get 8. So that means that this definitely does not qualify, because if you plug in one input, you get more than one output. In this case, we get 3 different outputs, 8, 3, and 7. So that does not qualify. So let's look for repeated numbers here in the x row. I don't see any repeated numbers. Let's look for repeated numbers in this x column. I don't see any repeated numbers. And let's look for repeated numbers here. I don't see any repeated numbers. Now notice that you have repeated numbers in the y column. That's okay. It's okay to get the same output from multiple inputs. So we get 2 for multiple inputs, -1, -5, 3. Here we get the same output for all kinds of different inputs, but that's okay. What disqualifies the table from being a function is if you have one input. For example, let's say that 7 produced 8, but it also produced 9, 10, 11, then that would disqualify the table as representing a function. Try number 12. When you come back, we'll do it together. Okay, we're back. So let's look for repeated numbers in the x row. We do have repeated numbers. So we have 7 and 7, but don't be tricked. The output is the same for both of them. So the fact that 7 is repeated does not disqualify that table from representing a function. Here we have a repeated number, but again, that does not disqualify the table because the outputs are the same. They're both green -10s. But 4 produces 2 different outputs. So that actually does disqualify the table as representing a function. We don't have any repeated numbers here, so we don't have to worry about that. We do have repeated numbers here, but they both produce 9, so that does not disqualify the table as representing a function. So if you got that one right, excellent. Okay, so notice that we represented a function with an equation. Those are the first problems that we did. For example, we had some expression f of x is equal to x squared plus 1, for example. So that's an example of a function represented as an equation. We also represented a function as a table. Those are the problems that we just did. We had our inputs, x, and our outputs, and we wrote all kinds of numbers so you can represent a function with a table. You can represent a function with an equation or a table, but the third way to represent a function is with a two-dimensional graph on the xy coordinate system, what we call the rectangular coordinate system. We learned that previously in this course. So the red graph is a representation of a function. The x values are considered to be the inputs. That's always the way it's going to be in the world of math. The horizontal axis is always representing the inputs of the function, and the outputs are the vertical movement. So let's say that you have a point here. The x value is the input and the y value is the output. So that's how we use graphs to represent functions. Now, again, a necessary characteristic of a function is that for every input, there can only be one output. So we disqualified a lot of these tables by showing that, for example, we plugged in 0, that one input, 0, but we got two different outputs. That's not allowed. That disqualifies the table as representing a function. Well, the way that we determine which graph can represent a function is by using what we call the vertical line test. These are functions because if we draw a vertical line, the line only touches the graph, the red graph, it only touches once. So for example here, the green vertical lines are only touching the red graph one time. So these are examples of functions. Same thing here. But if a vertical line touches a graph more than once, for example here, then this graph cannot represent a function. This is called the vertical line test. If any vertical line touches a graph more than once, then the graph cannot be a function. So this is a very easy test. So it says here, circle the relations below that cannot be functions. So we already found an example that cannot be a function. And maybe I should use a different color besides green. Now let's do a vertical line test here. Vertical lines only touch the graph one time. It gets a little steep in areas, but that can represent a function. And here, any vertical line only touches once, so that can represent a function. Now here, a vertical line touches multiple times, so that cannot be a function. That graph does not represent a function. And here, a vertical line touches more than once, so that graph cannot represent a function. Vertical lines only touch once, so that can represent a function. So again, this is just review. This passes the vertical line test. The vertical lines only touch the graph once. This passes the vertical line test. And this is kind of a tricky problem, but notice we have a closed dot and an open dot. So that would actually pass the vertical line test, and it would pass here. So any vertical line that you draw is only going to touch the graph one time. So that passes. So I want you to take a picture of these pages here, and I want you to try number 16. Draw vertical lines and make sure that those vertical lines only touch one time. If they touch the red graph more than once, that means that the graph cannot represent a function. So try 16. When you come back, we'll do it together. Okay, we're back. If we draw vertical lines at any place on the graph, the lines only touch the graph one time, so that passes. But here, vertical lines are touching more than once, so that cannot be a function. And obviously this cannot be a function either, because vertical lines touch the graph more than once. If you got that right, good job. Try number 17. When you come back, we'll do it together. Okay, we're back. So vertical lines touch the graph more than once, so that cannot be a function. Vertical lines only touch the graph one time, and same thing here. Vertical lines only touch the graph one time. So only the first graph can be disqualified from being a function. So if you got that right, good job. Try number 18. When you come back, we'll do it together. Okay, we're back. This one's a little tricky, but you can see if we draw a vertical line there, it actually touches more than once. So that's disqualified. This is not disqualified. You can draw vertical lines anywhere, and they're only going to touch once. Now this is a little tricky, but if you draw a vertical line right on top, you can see that it's going to touch an infinite number of places, so that does not qualify as a function. Or we can say it's disqualified. So if you got that right, good job. Okay, so again, we're still reviewing functions and function notation. This is very important review. So I want you to understand that function notation can take a lot of different forms. Even though the f of x form is the most common form, you can actually invent your own function notation. And you may see this on college entrance exams, or whatever exam or standardized test that you're taking. And this typically confuses students, so I just want you to be aware that you can actually come up with any type of function notation. For example, I'm going to make up this expression trapezoid x. I've got a trapezoid with an x inside, so I'll call that trapezoid x. Doesn't really matter what you call it, but I define trapezoid x to be x squared plus 90. X squared plus 90. So that's the operations that I'm defining for this function. So if somebody tells you to find trapezoid 3, what that means is you're going to plug in 3, or substitute 3 for x. So we have 3 squared plus 90. And so if our input is 3 into this function, the output is 99. Now we're asked to find trapezoid negative 2. So trapezoid negative 2 is negative 2 squared plus 90. How do I know that? Well, because I'm just copying this expression down. The only difference is instead of x, I'm writing negative 2. So then we get 4 plus 90, which is 94. Now we're asked to find trapezoid 7. So I'm just going to copy down that expression, except instead of x, I'm going to write 7. So now we get 49 plus 90, which is 139. And we're asked to find trapezoid negative 1. So that's negative 1 squared plus 90, which is 1 plus 90, which is 91. So again, you can come up with all kinds of different notation for functions. And sometimes you can have more than one input in a function. Now, you're not going to encounter this until you take your third course in calculus, vector calculus. But here I'm defining A, smiley face, B as this set of operations here. and we're asked to find -1 smiley face 5. So what that means is you plug in -1 for A, and you plug in 5 for B. So I plugged in those numbers. Whoops. I plugged in those numbers there. And we just calculate, and we can find our output. So -1 cubed is -1, and then 2 to the 5th is 32. So our output is 31. Alright, so now let's find 2 smiley face 6. So that would be 2 cubed plus 2 to the 6th power. So 8 plus 64, which is 72. -4 smiley face 1 is -4 cubed plus 2 to the 1st power. -4 cubed is -64, and 2 to the 1st power is 2. So then we get -62. 3 smiley face 3 is 3 to the 3rd power plus 2 to the 3rd power, which is 27 plus 8, which equals 35. Okay, so again, we're just demonstrating that function notation can take any form. So I want you to try number 21, and when you come back, we'll do it together. Okay, we're back, so we need to find triangle -2. You can call it whatever you want. So we're just going to plug in, or we're going to write this expression, but instead of y, we're going to write -2. So if you got that right, good job. Now we're going to find triangle 3. We're going to rewrite the expression up here. We're just going to replace y with 3. And so we can just write it as 4/3, or we can write it as 1 1/3. It doesn't really matter. In fact, I'm just going to leave it as 4/3 just to demonstrate that at this level of math, it's okay to write an improper fraction. Mathematicians don't really care. Okay, so triangle -1, that's just 4 over -1. So if you got -4, good job. Okay, so you may want to take a picture of the page at the right, and I want you to try number 22. Now we have 2 inputs. We have beta and we have omega. So you're going to plug in those numbers here. So try number 22. When you come back, we'll do it together. Alright, we're back. So we're going to plug in -10 for beta and 7 for omega, and we get -20 minus 35 is -55. So if you got that right, good. And now we're plugging in 3 for beta and 4 for omega. So we have 6 minus 20, which is -14. So if you got that right, excellent. So again, we learned that f is the most common notation for functions, but if we have 2 different functions or 3 different functions, then typically the letters we use are F, G, and H. So we've already learned this notation with the letter F. So if you want to find f of -6, and this is the function, we plug in -6. So in this case, we get 1 over 8 plus 12, which is 1 over 20. So we've already used that notation, but sometimes instead of F, you're going to see G. So let's try a problem where we have, instead of f of x, we have g of x. G of x is defined to be 4 to the x minus 1 in this example. And we're trying to find g of negative 2. So that means that our input is going to be negative 2, and our output is going to be whatever 4 to the negative 2 minus 1 power is. So I rewrote this expression, but instead of x, I wrote negative 2. So now we have 4 to the negative 3 power. We have to use exponent rule number 8. And then we just calculate 4 to the third power, which is 64. So if the input of our function is negative 2, the output is 1 over 64. And in this problem, the function is called g, whereas in the previous problem, the function was called f. So it says here, if h of x is x squared over 3, find h of 1.2. So we just plug in 1.2, or substitute x with 1.2, that is. And 1.2 squared is 1.44. Divide that by 3. And we get 0.48. So again, f, g, and h are the most common types of notation for functions. I want you to try number 26 and number 27 and number 28. You can do all three of these at once, and when you come back, we'll do them together. Okay, we're back. So if the input is 3, what is the output? The output is 10. So that's what we're doing here. We're looking for f of 3. If the input of the function g is negative 4, what is the output? Well, the output is negative 6 plus 10, which is 4. Now our function is called h. Here it was called f, here it was called g, and here it's called h. And this is saying if our input is 1/5, then what is the output? Well, 5 times 1/5 is 1, and the square root of 1 is 1. So if you got that right, good job. If you got all three of these right, excellent. Okay, so now we're going to something called piecewise functions. And piecewise functions are, well, you're going to see them in calculus courses and pretty much most of the primary upper math courses. So you're going to need to be familiar with these functions. They are very intimidating, but they're actually really easy. There are some things in math that are very intimidating, but they're easy. This is an example of that. So a piecewise function is a function defined by multiple expressions, in this case the green expressions, and each of these expressions, x minus 2 for example, has its own exclusive interval of inputs. So this part here, these go together, the green x minus 2 and the interval of inputs in purple, they go together. So what this means is that if x is between 1 and 5, the purple tells us if x is between 1 and 5, you use this expression to find your output. So if your input is between 1 and 5, you use this expression to find your output. But if your input is between 5 and 10, including 5 and 10, then you use this expression to find your output. So if your input is between 5 and 10, you use this expression to find your output. And of course it says equal to here. Actually, not 10 itself. I misstated there, not 10, but if x is 5, you'll also use this expression. If x is 10, then this function is not defined for that. So let's do some example problems. So we're asked to find f of 3. But the problem is we don't know if we use this expression to find the output or this expression to find the output. The output is f of 3, but do we use the blue equation or the green equation? Well, we don't know. But these intervals here tell us. So is 3 in this interval, or is it in this interval, or is it in neither interval? Well, 3 is obviously between 0 and 4. 3 is the input, and so the input is x, and 3 is between 0 and 4, so that means that we use this equation. So I'm going to highlight that. So I'm going to use this expression here, and I'm going to replace x with 3. So there you go. Alright, so now we're going to plug in 6 for our input, but notice 6 is not in this interval. 6 is in this interval. So that means that we use the green equation, or the green expression, excuse me. So 5 times 6 minus 1. So I rewrote this expression exactly, except I inputted 6. So again, this is all reviewed. These are things that we did in my intermediate algebra course. So now we're going to plug in 1. That's in this interval, so we know to use the blue expression. Now we're going to plug in 5. That's in this interval, so we know to use the green expression. 5 times 5 minus 1 is 24. Now we're going to plug in 8, so that's going to be in this interval, so we know to use the green expression. 5 times 8 minus 1 is 40 minus 1, which is 39. So again, that's how we evaluate or calculate the outputs of piecewise functions given certain inputs. Okay, so let's go to another example here. Now we have a different function, and it's a piecewise function because we use this expression if our x values are in this interval, if our inputs are in that interval. But we use this other expression if our inputs are in this interval. So f of negative 9, that's in this interval here. So we use the blue expression. So 1 over x plus 2, but x in this case is 9. So we get negative 1 over 7. Now negative 6, well, this is actually a trick problem, because notice it says that x is less than negative 6, but it does not say that it's equal to negative 6. So we're not going to use this blue expression. So let's see if we're going to use the green expression, but you can see that negative 6 is not in this interval either. So what do? Well, we don't do anything. The function's not defined for that input. So we say undefined. Okay, so now let's plug in negative 5. But again, negative 5 is actually in between this interval. And in case you're having trouble seeing that, write a number line. We have negative 10, we have negative 6, we have negative 4, and we have negative 2.1. So we use the blue equation when we're here, we use the green equation when we're here, but negative 5 is not in the blue or the green interval. Negative 5 is here. So the function is not even defined for negative 5. And maybe I should keep that there. So when it comes to negative 6, the previous problem, negative 6 was here, but we have an open dot on that because x is not equal to negative 6, it's less than negative 6. But we have closed dots everywhere else because we have less than or equal to, less than or equal to, and then we have less than, actually in that case it would be, in these cases it would be, well, yeah, you would pronounce those as less than or equal to. If you're reading left to right, we always read left to right when reading inequality symbols. So you don't have to write a number line, but you can do that if it helps you. And to be honest, I would recommend doing that if you don't have a lot of experience with these problems. So we're going to write undefined again. F of negative 2.1, well, it says x can be less than or equal to negative 2.1. So that means we can actually plug in to the green equation. Negative 2.1 cubed. And you can use your calculator for that. 2.1 times 2.1 and then times 2.1 again is 9. And this is going to be a negative number, 9.261. Negative 9.261. So I want you to try number 31, and when you come back, we'll do it together. Okay, we're back. So we need to know if we're going to use the blue expression or the green expression to find f of 9, the output if the input is 9. So 9 is between 7 and 100, so that means we use the green expression. So if the input of the function is 9, then the output would be 36. Now 5 is the input, and 5 is in this interval here, so that means we use the blue expression. So 3 plus 5, which is 8. 30 is in this interval, so we're going to use the green expression. So we have 4 times 30, which is 120. So if you got that right, excellent. Try number 4 here. Don't forget that one. 6.5 is in this interval, so we're going to use the blue equation, 3 plus x. 3 plus x, which is 9.5. So if you got that right, excellent. Okay, I want you to try number 32. Number 32 is going to be a little tricky, so be careful. You can draw a number line if you want to help you, and write open dots or closed dots and fill in the intervals, anything you want to do to help you. So try number 32. When you come back, we'll do it together. Okay, we're back. So negative 4 is in this interval. It's at the end point of this interval, because x can be greater than or equal to negative 4. So we would use this blue equation. So 1/2 times negative 4 is negative 2. So if you got that right, good. Now 8 is not in this interval,
And it's not in this interval either, and it's not at the endpoint of the interval, because it says x is less than 8, but it does not say that x is less than or equal to 8, which means that the function is really not defined for x equals 8. So if the input is 8, the function is not defined. So now our input is -6, and that's outside this interval. So again, just in case you want to picture this, -6 is out here, but our blue area is here. That's when we use the blue expression, and we use the green expression somewhere out here where we have 10 to 15. The distances here are not exactly accurate, but we don't really care about that. So if we plug in -6, we're not going to use the blue equation or the green equation. The function is not defined for -6. So we just say undefined. And what about 0? Well, 0 is actually in this blue interval here. So we use the blue equation. 1/2 times 0 is 0. So if you got that right, excellent. So far, we're just reviewing piecewise equations, or piecewise functions, because we covered these in my intermediate algebra course. But there's one thing that we didn't do in my intermediate algebra course. All of the problems that I gave you had intervals where the bounds were finite, but in this case, the bounds are actually indefinite. So we have a blue expression with interval restrictions, and a green expression, just like in the previous problems. Except in this case, we use the blue expression when x can be anything less than 2. So there's no limit to the interval when we're going into smaller and smaller numbers. We can go to negative infinity or approach negative infinity. So these problems are pretty much exactly the same as the problems we just did. There's just that minor difference. So we need to ask, where's 3? Is 3 less than 2, or is it greater than or equal to 2? Well, obviously it's greater than or equal to 2, or it falls in this scenario. It's not equal to 2, but it falls in that scenario. So we use the green expression. 4 times 2 to the 3rd power minus 8. So we have 4 times 8 minus 8, which is 32 minus 8. And 32 minus 8 is going to be equal to 24. Now 20, where does that fall? Is that less than 2, or is it greater than 2? Well, obviously it's greater than 2, so we're going to use the green expression again. Now that number is going to be really big, so we'll just leave it like this. 2 to the 20th power is going to be really, really big. Okay, what about f of -6? Well, -6 is less than 2, so we're going to use the blue expression. This is the first time that we're using the blue expression. Now, we have to use exponent rule number 8, so that's going to become 1 over 4 to the positive 6 power. And 4 to the 6th power is equal to 4096. So we have -7 over 4096 plus 1. And we can further simplify that. So that's going to be 4,089 over 4,096, and you can just leave it in that form for now. Okay, so let's try another one of these. So we have a blue expression and we have a green expression. So the question is -2 less than -3, or is it greater than 5? And the answer is it's neither. So the function is undefined if the input is -2. Now again, if you're having trouble seeing that, you can just draw a number line. In this case, we have -3 with an open dot because its x is less than, but not less than or equal to. If it's less than or equal to, then we fill the dot in. And x is greater than 5, so we use the green expression or we use the blue expression. And if anything falls in between here, which in the case of -2, it did fall in between there, then the function is undefined. Okay, so is 7 in the blue region, the green region, or the purple region? Looks like the green region. So we use the green expression, and we get 5 plus 14, which is 19. So there you go. Is -6 in the blue region or the green region? It's in the blue region. So what that means is the answer is 2. Now this is kind of confusing. Where did I get the 2 from? Well, what this blue expression tells us is that if our input is less than -3, our output is going to be 2. So you could plug in any input that is less than -3. It could be -3.1, -4, -5, -6, -1 billion. If your input is any number that is less than -3, the output is always going to be 2. It's just a constant number. So I know that's kind of confusing, but -6.01, same thing. Your input in this case is less than -3, so the output is going to be 2. So that's what it means, that there's just a constant there. So I want you to get a picture of these, and I want you to do number 35, and when you come back, we'll do it together. Okay, we're back. So is -2 less than -1 or equal to -1, or is it greater than -1? Well, obviously -2 is less than -1. So we're going to use the blue expression. So we have 1 plus 3 to the -4th power. Which is 1 plus 1 over 3 to the 4th power. So that's exponent rule number 8. Then we have 1 plus 1 over 81. And probably the easiest way to write that would be to just create a mixed number. So we have 1 and 1 over 81. So if you got that right, excellent. Okay, so now our input is -1. So is that going to be in the blue interval or the green interval? Well, it's equal. X is equal to -1 in this case. So it's going to be the blue expression that we're going to use to calculate the output of the function. So now we have 1 plus 3 to the -3. And that's going to be 1 plus 1 over 3 to the positive 3, so we used exponent rule 8 again, and then we have 1 plus 1 over 27. And so again, it's easiest probably to just write a mixed number. So 1 and 1 over 27. Okay, so now our input is going to be 0. So is 0 less than or equal to -1, or is it greater than -1? And the answer obviously is it's greater than -1, so we're going to use the green expression, and we get 4. So now our input is 12. That's going to be greater than -1, so that means we're going to use the green expression. So 12 plus 4 is equal to 16. So there you go. So if you got those answers, good job. Now try number 36. When you come back, we'll do it together. Okay, we're back. So the question is 7 going to be in the blue interval or the green interval? Well, 7 is greater than 4. So that means we're going to use the green expression. So we have 14 minus 3 is 11. So our input is now going to be 2. So where does that fall here? Well, it doesn't fall anywhere. If you draw a number line, we have 0 and we have 4. And by the way, these are both open dots. And the blue interval is here, the green interval is here, and the red interval means there's no definition, there's no output for the function. So 2 occurs here, which means that the function is not defined for that particular input. And what about -100? Well, that's going to fall in the blue region there, so we have to plug in -100 to that expression. So we have -100 squared plus 5 times -100 plus 1, and -100 times -100, that's going to be positive 10,000. And then 5 times -100 is -500 plus 1, so on and so forth. So we get 9,501. So if you got that right, good. So now we're going to review notation indicating operations between functions. If you see this notation here, it means f of x plus g of x. And if you see this notation, it means f of x minus gx and g of x, and so on and so forth. It's very important not to confuse f of x times g of x and f of g of x. We'll talk about that later. If you see a closed dot, then that's multiplication. If you see an open dot, that means it's a composite function where you're putting another function, or you're putting one function inside another function. So get a picture of this with your phone. Let's do some practice problems. It says if f of x is x squared plus 5x and g of x is 3x minus 2, find f plus g of x. So again, f plus g f plus g of x is just f of x plus g of x. Now, this is very confusing because we have all these parentheses, but remember with functions, function notation, parentheses doesn't always mean multiplication. So what is f of x? F of x is x squared plus 5x. And what is g of x? It's 3x minus 2. So we have this function that we're putting there, and we have this function that we're putting there. And so now all we have to do is simplify. So we have x squared plus 8x minus 2, and that is the answer. So that expression is f plus g of x. So let's find f minus g of x. Well, obviously that's just f of x minus g of x. And f of x, we're told, is the blue expression. And then we're going to subtract the green expression, but we're subtracting the whole green expression, not just part of it, so we have to use parentheses. One of the most common mistakes that students make is they don't write parentheses and they get the wrong answer. It's pretty much a guarantee that students are going to make that mistake. So now we distribute the negative symbol, so that's a positive 3x, so it becomes negative 3x. That's a negative 2, so it becomes positive 2. The signs change because we're subtracting. So now we just simplify and we get x squared plus 2x plus 2. So that is f minus g of x. So now we want to find f dot g of x. In other words, f times g of x. So that's just f of x times g of x. And f of x is the blue expression up there. And we're going to multiply by the green expression. So blue times green. And the problem doesn't tell us that we have to use FOIL. We could simplify that a little bit and use FOIL, but we really don't need to. It's not going to be a simpler form if we change this into a polynomial with the FOIL algorithm. So we can just leave it like that. Okay, so now we're going to find f over g of x, or f divided by g of x. So as you can imagine, that's just simply f of x over g of x. So this is not hard. So we take the blue expression and divide by the green expression, and we're done. Now we could simplify that a little bit because it is an improper fraction. How do we know it's improper? Well, because the degree in the top is bigger than the degree in the bottom. But I'm not going to make you change that to a proper fraction at this point. That's not really why we're doing this. We're just learning the notation. Okay, so I want you to get a picture of problem 37. And I want you to try number 38, part A. And when you come back, we'll do it together. Okay, we're back. So I'm going to make this expression yellow. And I'll make this expression purple, I guess. F plus g of x is just f of x plus g of x. F of x is x plus 1, and g of x is 3 to the x minus 6. So I'm just adding those together. So then we can simplify, and we get 3 to the x plus x minus 5. You can write the 3 to the x power after the x if you want. It doesn't really matter. So we got that right. Excellent. So go ahead and try part B, and when you come back, we'll do it together. Okay, we're back. So f minus g of x is just f of x minus g of x, as you can imagine. So that's just x plus 1 minus, and we have to use parentheses. It's almost a guarantee, like I said, that students are going to not write parentheses there, and you're going to get the wrong answer. So we have to distribute the negatives, so that's a positive 3 to the x, so it becomes negative 3 to the x. That's a negative 6, so it becomes positive 6. You're subtracting, so the signs change. So now we're left with negative 3 to the x plus 7. So if you got that right, excellent. Okay, go ahead and try part C. When you come back, we'll do it together. Okay, we're back. So now we're trying to find f of x times g of x. F of x is x plus 1. G of x is 3 to the x minus 6. So we're just multiplying the yellow and purple expressions, and I'm just going to allow you to leave it in that form. We don't really have to, use the FOIL algorithm. That's not the point of these problems. If it's easy to simplify, great, but if it's not easy, then you don't have to waste your time simplifying for these particular problems. Okay, so try part D. When you come back, we'll do it together. Alright, we're back. So f over g of x is obviously f of x divided by g of x, which is x plus 1 over 3 to the x minus 6. And that's pretty much it. We don't really need to simplify that anymore. So if you got that answer, excellent. Okay, so now we're going to move on to composite functions. Let's try 39. So we have some expressions again, and I think I'll color this expression orange, and this expression maybe I'll try purple. So this expression is just a different way of writing f of g of x. So what that means is you're plugging in the g of x function into the f of x function. So one way to write that is you can take the g of x and just turn it into the purple 6x. You don't have to do it that way, but that's just one way to demonstrate what we're doing. So now f is x plus 1, right? F of x is x plus 1. So instead of plugging in x, instead of using x as our input is actually going to be 6x. So instead of x plus 1, it's 6x plus 1. And that is the answer. So this is pretty easy. Let's try part B. We're doing the same thing, except instead of putting the g function into the f function, we're putting the f function into the g function. So it's kind of the other way around. Now we know f of x is x plus 1, so I'm just going to plug that in there. So it's x plus 1. And so now we're just trying to find g of x plus 1. So what this means is we're going to write 6x, but instead of x, you see the green x, instead of x, we're going to enter x plus 1. There's a lot of different ways to think about this. So I'm writing the purple expression, but instead of x, I'm writing x plus 1. I just substituted x plus 1 for x. Again, a lot of different ways to think about this. But you need to get used to how to do this type of problem. These are called composite functions. Okay, so let's do one more of these problems before you try one on your own. Sorry, my computer's going kind of slow here. So now we have different functions. We have this green function here, and we have this red function here, and we're looking for f of g of x. That's what that means. Now we know that g of x is 5x, so I just replaced g of x with 5x. That's what it equals. So now what we're doing is we're plugging in 5x into the f function. So instead of x minus 2, it's 5x minus 2 cubed. Plus, instead of plus x, it's plus 5x. So do you see that I replaced x with 5x in these regions here? Can't really find something to highlight that. So that is the answer. Now let's look for g of f of x. So we're plugging in f into the g, and f of x is, this might be better to use brackets. You don't have to use brackets, but it makes it a little easier to see what's going on. So f of x is x minus 2 cubed plus x. So I took that green expression and put it in here. Now we want to take that whole green expression and substitute it for x in the g of x function. So we have 5 times, and I probably should use brackets, 5 times x minus 2 cubed plus x, then end bracket. Okay, so we can distribute. Just to simplify a little bit, I guess. And there you go. So that is g of f of x. And there you go. So I want you to try number 41. See what you can do. And I'm going to leave 39 and 40 in the window. and when you come back, we'll do it together. Okay, we're back. So I'm going to use blue and green for the functions. So f of g of x is what we're looking for. And we know that g of x is negative 2x. So I just plug that in for g of x. And now we go to the blue expression. We have 9. F of x is 9 over 6 minus x. But instead of x, we're going to write negative 2x. So we replaced x with negative 2x. And so that's going to be 9 over 6 plus 2x, because that's a double negative. And that's really all you can do with that. So if you got that answer, excellent. Okay, so go ahead and try part B, and when you come back, we'll do it together. Okay, we're back, so we're trying to find g of f of x. And f of x is the blue expression. So I'm going to plug in the blue expression, 9 over 6 minus x. And now we're going to go to the green expression, negative 2 times x. But instead of x, it's 9 over 6 minus x. And so then we get negative 18 over 6 minus x. Now I know what you're thinking. You're thinking, let's reduce that. Let's reduce the fraction. 18 divided by 6 is 3, right? But the problem is you can only reduce if we have a 6 in front of the x here also. Then we could reduce this to 3, and these would reduce to 1. But we don't have a 6 in front of the x, so we can't reduce that. So if you got that right, excellent, good job. And one thing you can do to simplify this, by the way, is you can take this negative and you can put it in the denominator, and you can get 18 over x minus 6 like that. That's actually a simpler way to write that. That would probably be better. So let's move this up a little bit and write that in the simplified form. Okay, go ahead and try 42, and when you come back, we'll do it together. All right, we're back. So I'm going to make this expression pink, and the other one I'll make green. And we want to find f of g of x. G of x is 2 to the x plus 1. So I plugged in the green expression, and so now we're going to write the pink expression, except wherever we see an x, we're going to write a 2 to the x plus 1. So instead of x squared, we have 2 to the x plus 1 squared. And instead of 4x, we have 4 2 to the x plus 1. And so on and so forth. So then we just write minus 1. And at that point, we're pretty much done. We could simplify a little bit, but that's good enough. That's f of g of x. So now we want to find g of f of x. So go ahead and try part B, and when you come back, we'll do it together. Okay, we're back. So I'm going to put the f function inside the g function. So there you go, and I'm going to write the green expression, but everywhere where I see an x, instead of writing x, I'm going to write x squared plus 4x minus 1, and this is in the exponent, so you have to write a lot bigger. So I plug that in there. So that is the answer. We don't have to really simplify any more than that. So, if you got that right, excellent.
Okay, so that was the class today. If you want to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and 4 and 5 and 6, 7, 8, 9, and 10. But don't go before you get the homework. Remember, the homework is not optional. Here's screenshot number 1 of the homework assignment, and number 2, and screenshot number 3, and number 4, and number 5, and number 6. But don't go before you get the answers to the homework. Remember, it's not enough just to attempt the homework. It must be done completely and correctly. Here's the answers. And the second set of answers. So get that homework done completely, correctly, neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.